we search the leftmost child, we go to C, and after that to A. The goal is not exist, come back to F, and now we can find G. It is a good idea for expansion because the necessary memory is related to some branches that are searched by ourselves. The branch in this range are saved in the memory, but the information of other branches is not necessary to consider. Because of that, DFS is a good algorithm based on the space complexity. BFS is another way to search. In this example, we try to use a queue for saving the neighbors of any node. We start from level or limit 1, including the sourcing source node. Check the neighbors, DEP. It is in level 1 or limit 1. Again, we consider the neighbors of D, E, and P and save all of the information of this new level of the nodes in the queue and continue this iterative manner until receiving goal. If goal is meet at level K, we terminate. Because of that, BFS can find a goal with optimal path. As you see, in BFS, when you receive a goal in one level, the cost is the summation of the levels. And because of that, BFS is optimal algorithm. Why? The previous DFS algorithm is not optimal and can find goal in deeper branch instead of in optimal branch. However, BFS needs to save all of the information of the different nodes in different levels. Because of that, in the worst case, BFS needs to save the information of all nodes. That is very, very great. It is exponential. In this criteria, BFS is worse than DFS, but because it can find the optimal solution, it is better to hybridize BFS and DFS. The hybridization of BFS and DFS is iterative deeping. As you remember, in iterative deeping, we started from level 1 or limit 1, and in this step, we search DFS. By usage of DFS, you can guarantee to find the least amount of the children to find the goal. And because your limit extends one by one, it's possible to find the optimal solution similar to BFS. It is a good idea for extending algorithm based on the advantages of more than one algorithm. And we are ready to consider the cases with different costs for actions. We assume that the links corresponding to the actions is given with a cost, and the costs are non-negative. We just consider the positive or zero weights. For this kind of the searching problem, we use a priority queue. In the priority queue, we save the nodes with respect to their labels. To define the labels, for S, the label is 0. For the child of S, the cost of the link between S and D is added to label S, or label of the predecessor node. The predecessor node of D is S. The predecessor of E is S. The predecessor of P is S. Thus, the label can be defined by a unique formula. In this formula, the label of any node is the sum of the cost associated with the action or link between the predecessor node and the current node, plus the label of the predecessor. For example, for D, the cost of link is 3, plus the label of the predecessor is 0. 3 plus 0 is 3. Also for B, the cost of the link between D and B is 1, and the predecessor label is 3. 3 plus 1 is 4. This formula can be used for all of the nodes in a loop. Now, for uniform cost implementation, we started from S and continue a greedy searching algorithm. In a greedy searching algorithm, every node with the least label is chosen for the best exploration. For example, between the neighbors of S, D, E, and P have the labels 3, 9, and 1. The best is 1. We select P for exploration. P has a child, Q. The cost between P and Q is 15 plus the label of P is 1. 1 plus 15 is 16. But instead of searching Q, we compare the label of Q with E and D. Which of them has the least label? D. Because of that, we left Q and focus on D. The cost of the neighbors of D are 4, 11, and 5. Which of them the best? B is the best. We consider the neighbor of B. The neighbor of B is A. The cost between B and A is 2. 2 plus the label of B, 4, is 6. The label of A is 6. Again, we compare the label of A with C, E, and Q. The best one is E. We focus on E. The neighbors of E is H and R. E to H has 8 cost. 8 plus 5 is 13 for H. And for R, the cost is 1. And 1, sorry, is 2. 2 plus 5 is 7. Again, we compare the cost. 7 is the best. We continue from this node. The neighbor of R is F. The label is 8. 8 less than 11 and 60. We continue from E. The neighbors is C and G. C is 11 and G is 10. 10 is the least among 11 and 17 and 11 and 16. Because of that, we can terminate the searching process in G. If there is a better label for another node, we continue that label and the corresponding node to find the better solutions. As you see, the implementation of the Uniform Cost Search, or UCS, is based on a priority queue that needs log n computation for choosing the best location for any new state to augment in the priority queue, and UCS can find optimal solution for both of the graph with equal costs and the graph with variable costs for different links. And it is possible to define the object-oriented models where the object save their labels inside, and in the queue we connect the nodes with respect to greatness of their labels. Now we are ready to extend our searching algorithm to the informed search. In the informed search, at the first, we try to define an estimation from the current node to the goal state. The name of this estimation is heuristic. Based on the heuristic, we define a greedy search algorithm. We discuss about the advantages and disadvantages of this greedy search algorithm. Then we extend a star search for the tree and the corresponding graph search for the graph. And we show that the similarity between informed search and previous discussion on uninformed search. Do you have any problem in the uninformed search? Is there any ambiguity in the uninformed search? Because we can start the informed search. Before that, you can ask me any ambiguity. No problem? No question? Thanks so much. Starting from heuristic. In the searching problem, we face with continuous and discrete environment. In the continuous environment, the calculus definition about the function, about the limit, about the distance, about the norm can be used. But in discrete environment, again, we can use the corresponding formula of calculus in discrete manner. This means that in the discrete environment, temporarily we forget the discrete environment. For example, in this example, there is a binary matrix to show the environment as the square space. This matrix contains 1 and 0 to save the location of the agent, and the same can be do for the goal. Now, instead of using discrete movement, it is possible to use mathematical distance from the calculus to define an estimation from the location of the agent and the goal. This estimation can be implemented by a straight line, forward or backward. And also, we can move up or down. If you use the straight line, you define a Manhattan distance between the nodes and the states. For Manhattan distance, for example, if your location is x1 and y1 and the goal location is x2, y2, at the first you can define the difference between your x and the goal x. It can be defined by the absolute of x2 minus x1. And again, for moving down, you can define the difference between y value of yours and y value of goal state. The difference between y axis is absolute of y2 minus y1. Its absolute is 5 and the absolute of x is 10. 10 plus 5 is 15 as the Manhattan distance between the agent and the goal. As you see, this cost is an estimation for traversing between the agent place and the target. But it is not real cost because for moving to the goal, you have some additive cost for traversing a path to the goal. But this estimation is useful to compare the location of different nodes in the space and choosing the best one for extension. And also, Euclidean distance can be used. In Euclidean distance, the quadratic difference between x2 and x1, x2 minus x1, power 2, plus the similar term for y2 minus y1, power 2. Uh, the sqr root of this value is Euclidean distance. In this example, 11.2. That is less than Manhattan distance between the source and target, but both values are heuristics because both values estimate the distance between the agent and the goal state. This simple example shows that the heuristic is not unique, and you can define the heuristic with different kind of distances and norms. All of them are heuristics. If you are familiar with different distances, you can define the different heuristic with respect to your task. That means heuristic is task dependent, and based on the different tasks, we can define the different heuristics. Are you okay? Do you have any problem? No one? No question?
No problem, doctor. No problem, doctor.
Cheers. Another example. Uh, we come back to the Romania roads. We add a new table containing two columns. In the first column, the name of the city are saved. In the second column, the distance of a straight line between any node and Bucharest are saved. This means that we have started from Bucharest. The estimation of distance between Bucharest and itself is 0. For other nodes, we connect the nodes with Bucharest with a straight line and we calculate the distance as the estimation of the path between any node and Bucharest. For example, for Arad, we draw a line between Arad and Bucharest and calculate the distance. In this example, this is 366. The same for Kravia. For the Kravia, again, we connect this node to the Bucharest and calculate the distance. The distance is 160. The same process is doing for all of the nodes. And now we have a heuristic hx between any state and the goal state. As you see, this heuristic is task dependent. It is related to the location of Bucharest. If your problem changed to finding a path between the Arad and Vasily, for example, this heuristic is not useful, and you should define some new straight line between Vasily and other nodes and evaluate the distance over the straight line. This shows that heuristic is completely related to the task. Now, we remember that uniform class process searched the node with respect to list label. Now, based on the hx, we have some new labels for the nodes. And we can continue the searching with respect to this value. Please follow me. This greedy algorithm is a simple way to search the different graph and trees. Now we use greedy search on our example. Our example is started from Arad. Arad has 3 neighbors. The best neighbor of Arad with respect to hx is Sibiu because Sibiu label is 253. That is less than Kilimesra and Zarin. Because of that, instead of searching these neighbors, we focus on Sibiu. Please pay attention to the table of heuristics. Again, for CBO, we have 4 neighbors, but with respect to paragraphs H, 178, that is the least between 366, 380, and 193. We focus on the paragraphs. Again, we expand the paragraphs neighbors. The paragraphs neighbors is again Sibia and Bucharest. We come back to the heuristic table. The Bucharest label is 0 and Sibia has 253. The least one is Bucharest, and Bucharest is the goal, and we stop the searching process. As you see in this example, by using just the heuristic values as the label, we can find the goal. But is the path from the starting node to the Bucharest is optimal with respect to this greedy algorithm? The response is negative. Greedy algorithm, as mentioned in theory of algorithm, does not guarantee to find the optimal solution. There are some exception about optimality of greedy algorithm. For example, when you try to cover a graph with a tree, you have two important algorithms, prime and Kruskal. Both of the are greedy search. But both of the algorithms can find optimal tree or minimum spanning tree for the graph. But they are just exception, not true for all of the tasks. Thus, greedy algorithm, although is simple and for implementation the simple algorithm is better, but because they have not guaranteed to find the optimal solution, we prefer to use this algorithm in some part of the final implementation and hybridize this algorithm with other algorithm just for improvement of the result. If you are interested to combine this greedy search with our previous discussion about the uniform cost search, as you remember, in those implementation of uniform cost search, You use GN as the cost or label for traversing from a starting node to the final node or middle nodes. And by heuristic, you can estimate the path cost between any middle node to the target. We combine these two parts. The first part, try to find a path from the source to the target and find good path from the source to the middle node. And by the heuristic, you can define the reasonable path between middle node and the target by choosing the nearest distance or nearest heuristic in your problem. If you combine this cost, you can define a star search. A star search is a new kind of the greedy algorithm that combines two costs and one cost is computationally and the second one is estimation. We refer to the first one as the backward cost. Backward cost means the cost of source or a starting state to any middle state. This is backward cost and denoted with Gn. And the heuristic is a forward cost because estimate the path cost between any node and the goal. We denote it with Hn. Now, the summation of Gn and Hn is denoted with Fn and it's used by A star search. Consider this simple example. As you see, for any node, we have an estimation denoted with H. For example, this the estimation of the path between S and goal is 6, and between A and G is 5, etc. At the initial state, S, the backward cost is 0, and the heuristic cost is 6. F is 6. We have a single option, A. The cost is 1. 1 plus 0, G is updated as 1. And value of H is 5. For memorizing G and H for unknowns, we define an object instead of any node and define G, H, and F as the entities of the object and update every node with respect to traversing process. For example, for neighbors of A, B, D, and E, we define 3 objects. For G, the cost between A and B is 1 plus the predecessor G is 1. 1 plus 1 is 2. And the heuristic for B is 6. We update H value. And the summation of G and H is 8. F value of this object is updated. The similar process happens for D and for E. Now, we compare F value. F value of B is 8, the F value of D is 6, and F value of E is 10. D is better. We focus on D. The child of D is G. We add a new object instead of G. The value of G is updated. The cost is 2 plus G value of D is 4. 4 plus 2, 6. G is 6. And heuristic of G is 0. We update this. Now, compare a value of G and other nodes. B has F value equal to 8. E has F value equal to 10. And G has a value equal to 6. 6 is the least. Because of that, we can terminate the search. Is it possible to improve the value of cost, optimal cost? The response is negative because the F value of B is greater than G. The same happens for E. Because of that, continuing B or E cannot provide better solution. But is it okay for all of the implementation? The response is not clear, and we need more example. Before considering more example, if you have any problem, you are free to ask me, or if there is any ambiguity, please ask me about your question. No problem? Now, we consider the second example. As you see in this example, we start from S. We define 3 columns. First column for G, the second column for H, and the third column for the F, or the summation of G and H. For S, G is 0, H is 3, and the summation is 3. There is no other option. We continue with expanding the neighbors of S. The neighbor of S is A and B. We write SA and SB. We update G and H. G is 2 plus 0. G of A is 2. H is 2. It is safe associated with node A. We write 2. 2 plus 2 is 4. A value is 4. Again for B, the cost is 2. 2 plus 0 is 2. Again, G value of this pass is 2. And the heuristic of B is 1. We save in each column the value of 1, and the summation is 3. Now, we compare a value of the first option and the second option. 4 is greater than 3. Because of that, we focus on B. The neighbor of B that is expanded by B is G. S, B, and G. For updating G and H, we see that the cost between B and G is 3 plus G of B is 2. 3 plus 2 is 5. And the heuristic for G is 0. 5 and 0. The F1 is 5. If 5 is compared with 4, we need to check the neighbors of A because the cost of SA is 4, that is less than 5. And we have an opportunity to find better solution by continuing A. The neighbor of A is G again, and G is updated with 2 plus 2, that is 4, and the heuristic is 0, and the sum of G and 0 is 4. 4 is better than 5, and there is no other option to consider. Terminates when it receives to S to G with 5. This shows that ASI is not optimal. What's the reason? Really? Because there is not a unique heuristic for any task. We cannot guarantee to find optimal solution by A star with respect to any heuristic. That means heuristic is very important in the convergence of ASR to the optimal solution. We need to limit our attention to some kinds of the heuristics instead of proving the optimality of ASR with respect to all kinds of the heuristics. Because of that, in the next lecture, we focus on some special kinds of the heuristics, namely admissible heuristics, and prove the optimality of ASR happens under admissible heuristic. For non-admissible heuristic, we cannot guarantee to find optimal solution by ASR. But the definition of such special heuristic is left to the next lecture. Thank you, everybody. I'm ready to respond to your question.
Thank you, Dr.
Never mind. It's my pleasure.
Merci.
Thank you, everybody. You can go to the lecture in the courses, and also the video will be uploaded soon for yourself. I think there is a duration time between the class and uploading the course. I think after 1 day, you can access to the lectures in the same LMS home. I hope you enjoy from this course and have the best in Iraq and in Iran. For the Monday, we have the same class. If you are in Tehran, I'm in department and we have similar meeting in the classroom. But if you are in Iraq, we use the same system for presenting the lecture and respond to any question that you are faced with it. Thank you, everybody.
Thank you, Doctor.
Hope the best of the best. Goodbye.
Goodbye.
Goodbye, Doctor.